loco boiler built around a molten chloride salt-fast reactor. A molten chloride salt-fast reactor, or MCSFR, is a type of Generation 4 nuclear reactor designed to be simple and very safe to operate thanks to the molten salt's very high boiling point and its natural ability to moderate the nuclear reaction by temperature due to thermal expansion. Despite the relative safety and potentially lower cost of molten salt reactors, they have often struggled to gain traction since the original molten salt reactor experiments in the 1950s and 60s. This is most likely due to non-forward-thinking policies implemented in the past, which has caused a general reliance on other less efficient and potentially more expensive nuclear reactors. As you can see, I have included a meter rule to indicate the scale. In this case 1 centimeter equals 1 millimeter, as a meter rule is 100 centimeters long. However, it is portrayed as 100 millimeters long in this drawing due to the scale. Here is the reactor boiler design. As you can see, inspiration has been taken from oil tanker trucks where the corners are rounded. I haven't yet figured out how to display this on the cross-section. The reactor is split into two sections, with the top section made entirely of neutron-reflecting material while the bottom section is made entirely of neutron-absorbing material. As per standard molten chloride salt-fast reactor design, the fluid would be pumped from the lower section to the upper section, while internal pipes allow the fluid to flow down to the lower section via gravity. Due to the different materials making up each section, the fluid can be moderated by the speed of the pump, thus in a power cut the reactor would automatically shut down. This, combined with the moderation caused by the thermal expansion of the fluid, would prevent meltdowns from occurring. As you can see, the two sections are currently identical to ensure they have the same volume. The idea is that sufficient fluid must be provided to fill either the top or bottom sections when in use. The holes that go all of the way through represent tubes that allow reactor heat to be transferred to the coolant loop or steam, depending on design. In both cases, the molten salt or water steam enters the reactor at the lower section where it absorbs the decay heat energy before being pumped up to the upper section where it absorbs the heat of the actual reaction. Clack check valves prevent backwards flow. This system allows for preheating of the fluid to reduce the likelihood of thermal shock occurring in the pipes. The lead shielding is a snug fit around the outside of the reactor to increase its thickness and reduce the intensity of the gamma radiation. In this current example, the lead shielding is 6 cm thick, meaning that the gamma radiation released is around 1/16 of the intensity inside the nuclear reactor. However, I do not know if this would be sufficient or not. The outer metal casing represents the steel sheet on the outside of the boiler. This dimension was taken from the smallest size loco boiler diameter used by the Great Western Railway of 3 ft 9 inches. Current calculations suggest that the internal volume of each section for the molten salt fluid is around 200 to 300 liters depending on wall thickness. External pipes will be needed in order to comply with existing legislation and allow connections to existing infrastructure. I will now go into detail as to how I designed each section. The reactor shielding was designed by drawing a cylinder at the maximum possible outside diameter of the shielding and then removing the section pre-allocated for the reactor. As the boiler is currently in a simplified form, I have not built the shielding over the ends of the reactor so people can see how the reactor was designed. As I said earlier, the pipes are represented by the holes that travel all of the way through the reactor. Their location was governed by an approximation based around the center line and the outside diameter of the reactor. These pipes would be made out of their respective neutron-absorbing reflecting material for each section. Each section was designed by rounding the outer corners of two semi-cylinders. As I said earlier, I haven't figured out how to round the corners of the cross-section. Each of the two sections would be entirely made of their respective neutron-absorbing reflecting material with regards to their purpose to help moderate the reactor. If the reactor is to be used to directly heat water steam, the boiler may have to be optimized for producing flash steam due to the reactor's high operating temperature, with a maximum temperature of 600 degrees Celsius. This is because at such high temperatures, all liquid water will spontaneously boil into steam unless the boiler is kept at such high pressures that the water steam becomes supercritical. I should probably finish off by mentioning that I have no experience in nuclear technology except from what information I have learned from free online services. I have slightly more experience with steam technology, however I know that I have a lot to learn.
Oh, and by the way,
thank you for watching. Please feel free to leave comments below and subscribe to the channel for future episodes. In fact, you have to subscribe.
Resistance is futile.